Associativity, commutativity, and semigroups. Let star be a binary operation on a set S. We say that star is associative in S if for all x, y, z in S, we have x star y star z equal to x star y star z. Notice how the parentheses appear in different positions on each side of this equation. A semigroup is a pair S star where S is a set and star is an associative binary operation on S. Let's look at an example. Let S equal the set consisting of A and B and define star using the following multiplication table. Since all four outputs are A or B, we see that star is a binary operation on S. Is star associative in S? One way to answer this question is to check if x star y star z is equal to x star y star z for all possible combinations of x, y, and z being equal to A and B. For example, we have A star B equal to A star B because A star B is equal to A according to the multiplication table. And again, A star B is equal to A according to the multiplication table. And we also have A star B equal to A star B, right? Because B star B is equal to B according to the table. And then A star B is equal to A. So both of these computations came out to be the same. They're both A. Right? So A star B is equal to A star B. It is important to be aware that verifying a single instance of associativity is not enough to show that an operation is associative in a set. All possible instances must be verified. So here's what it looks like when we verify all possible instances. Notice that there are 8 instances in total. And these computations prove that star is associative in S. Therefore, S star is a semigroup. I would recommend pausing the video at this time and checking all these computations for yourself so that you're fully convinced that we do in fact have a semigroup here. It's worth noting that for this example, there is a much less tedious way of verifying that star is associative in S. Consider the multiplication table for ordinary multiplication on the set 0, 1. Observe that this table is identical to the one above it, except that all the names have been changed. We replaced each instance of A with 0 and each instance of B with 1. It follows that we can see that star is associative in AB simply by recognizing that multiplication is associative in 0, 1. Let's look at another example. Let S equal the set consisting of A, B, and C and define star using the following multiplication table. Notice that A star B star C is C star C, which is B, and A star B star C is A star A, which is equal to B. Right, so A star B star C is equal to A star B star C. However, again, this single computation does not show that star is associative in S. And in fact, this time we have the following counterexample. A star C star B is equal to C star B, which is equal to B, and A star C star B is equal to A star B, which is equal to C. Thus, A star C star B is not equal to A star C star B. So star is not associative in S, and therefore S star is not a semigroup. Let's try an exercise. Each of the following is a multiplication table for a binary operation star on the set S equals set containing A and B. Determine if star is associative in S. Now's a good time to pause the video, try these problems yourself, and then resume the video to check your answers against mine. For the first one, the answer is yes, because all of the outputs are A. It doesn't matter what inputs you choose, you will always get A. Specifically, X star Y star Z will always be A, and X star Y star Z will always be A. Here we're replacing X, Y, and Z by various combinations of A's and B's. The second one, the answer is no. We could come up with a counterexample here. For example, B star A star B is A star B, which is equal to B, whereas B star A star B is B star B, which is equal to A. For the third one, the answer is also no. Here's a counterexample. A star B is equal to B star B, which is equal to A, and A star B is equal to A star A, which is equal to B. The last one, the answer is yes. Whenever you do a computation here, you always get the one on the left. A star anything is A, and B star anything is B. That's why this works. So X star Y star Z is just X star Z, picking the one on the left, which is X, again picking the one on the left. And X star Y star Z is equal to X because X star anything is X. So in both cases, we get whatever the leftmost input is. Let's look at some more examples. The set of natural numbers together with addition, the set of integers together with addition, the set of natural numbers together with multiplication, the set of integers together with multiplication. These are all semigroups. Addition and multiplication are both associative in the set of natural numbers and in the set of integers. Another example, the set of integers together with subtraction. Let's do a computation. 1 minus 2 minus 3 is equal to negative 2 minus 3, which is negative 5, whereas 1 minus 2 minus 3 is 1 minus negative 1, which is 1 plus 1, or 2. Subtraction is not associative in the set of integers. Therefore, the set of integers together with subtraction is not a semigroup. Associativity is closed downwards. By this, we mean that if star is associative in a set A and B is a subset of A, then star is associative in B. The reason for this is that the definition of associativity involves only a universal statement. This is a statement that describes a property that is true for all elements without mentioning the existence of any new elements. A universal statement begins with the quantifier. This upside down A is read for all or every, and never includes the quantifier backwards E is read as there exists or there is. As a simple example, if every object in set A is a fruit and B is a subset of A, then every object in B is a fruit. The universal statement we are referring to might be for all of X, P of X, where P of X is the property X is a fruit. In the case of associativity, The universal statement is for all x, for all y, for all z, x star y star z is equal to x star y star z. Let's look at another example. Let 2z be the set of even integers. Is 2z together with multiplication a semigroup? The answer is yes. When we multiply two even integers, we always get an even integer. Therefore, multiplication is a binary operation on 2z. Since multiplication is associative in z and 2z is a subset of z, it follows that multiplication is associative in 2z. Here we're using the fact that associativity is closed downwards. So 2z together with multiplication is a semigroup. As another example, is 2z together with addition a semigroup? Again, the answer is yes. When we add two even integers, we always get an even integer. Therefore, addition is a binary operation on 2z. Since addition is associative in z and 2z is a subset of z, it follows that addition is associative in 2z. Again, using the property that associativity is closed downwards. So 2z together with addition is a semigroup. As another example, let's look at 2z plus 1, the set of odd integers. Is 2z plus 1 together with multiplication a semigroup? The answer is yes. When we multiply two odd integers, we always get an odd integer. Therefore, multiplication is a binary operation on 2z plus 1. Since multiplication is associative in z and 2z plus 1 is a subset of z, it follows that multiplication is associative in 2z plus 1. So 2z plus 1 together with multiplication is a semigroup. How about 2z plus 1 together with addition? Is that a semigroup? The answer to this one is no. When we add two odd integers, we always get an even integer. For example, 1 plus 1 is equal to 2. So addition is not a binary operation on 2z plus 1. Therefore, 2z plus 1 together with addition is not a semigroup. Let's try another exercise. Determine if each of the following is a semigroup. And now's a good time to pause the video, try these problems yourself, then resume the video to check your answers against mine. Okay, the first one is the set of natural numbers together with star, where a star b is equal to a. So we're choosing the one on the left. The answer to this one is yes. Let's check the associativity. A star b star c is equal to a star c, right? For a star b, we're choosing the one on the left. We're choosing a. And then for a star c, we're choosing the one on the left. We're choosing a again. And that's equal to a star b star c, right? Because a star anything is always a. We're just choosing the one on the left. Okay, this is true for all a, b, c in the set of natural numbers. Second one, the set of positive integers together with star, where a star b is equal to a to the b, meaning multiply a by itself b times. The answer here is no. Let's look at a counterexample. 2 star 1 star 3, that's 2 to the 1 to the 3, which is 2 to the 3, which is 8. Whereas 2 star 1 star 3 is 2 to the 1 to the 3, which is 2 to the 1, which is 2. We got two different answers. For the third one, the set of integers together with star, where a star b is the minimum of a and b, the smaller of a and b. As a hint, you may want to check 6 different cases when trying to determine if a star b star c is equal to a star b star c. For example, one such case would be a less than or equal to b less than or equal to c. Another such case would be a less than or equal to c less than or equal to b. The answer to this one is yes. Let's give ourselves some room here. The first case is A less than or equal to B less than or equal to C. Let's do this one in detail. A star B star C is the minimum of A and B star C, which is A star C, right? Because the minimum of A and B is the smaller of A and B, and we're assuming that A is less than or equal to B in this case. So A is the smaller one. Similarly, A star C is the minimum of A and C, and we're assuming that A is less than or equal to C, so that's equal to A. Now, A star B star C is A star the minimum of B and C, and that's A star B, right? The minimum of B and C in this case is B because we're assuming that B is less than or equal to C. Then A star B is minimum of A and B. And again, since we're assuming that A is less than or equal to B, that's equal to A. So you can see that in case one, both computations match up. They're both equal to A. Okay, the second case would be A less than or equal to C less than or equal to B. And here are the computations. Case 3, we have B less than or equal to A less than or equal to C. Case 4, B less than or equal to C less than or equal to A. Case 5, C less than or equal to A less than or equal to B. And case 6, C less than or equal to B less than or equal to A. Okay, now's a good time to pause the video another time and check all these computations carefully. Spend a little time and go through them carefully to make sure that you understand how all of this is working. Associativity allows us to add and drop parentheses as we like. For example, since addition is associative in n, the expression 1 plus 3 plus 6 makes sense. Indeed, it doesn't matter if we think about 1 plus 3 plus 6 as 1 plus 3 plus 6 or 1 plus 3 plus 6. In each case, we get an answer of 10. More generally, if star is associative in a set S, then for A, B, C, and S, we can write A star B star C with no parentheses without worrying about it being unclear. Let star be a binary operation on a set S. We say that star is commutative or abelian in S if for all x, y in S, x star y is equal to y star x. Let's look at an example. Let S equal the set of AB and define star using the following multiplication table. We have already seen that S star is a semigroup. Is star commutative in S? The answer is yes. This follows from the following computations. A star B is equal to A, and B star A is equal to A. Visually, we could check commutativity by drawing a diagonal line down the main diagonal of the multiplication table and checking that we have symmetry across this line. Notice the two A's across the diagonal line there. It's acting as a mirror, and since both of those elements are equal, we see that we have commutativity. So S star is a commutative semigroup. Some more examples. The set of natural numbers together with addition, the set of integers together with addition, the set of natural numbers together with multiplication, the set of integers together with multiplication. These are all commutative semigroups. Addition and multiplication are both commutative in the set of natural numbers and in the set of integers, as well as being associative. Some more examples. 2n together with addition, 2z together with addition, 2n together with multiplication, and 2z together with multiplication. These are all commutative semigroups. Here we use the following facts. Addition and multiplication are both commutative and associative in the set of natural numbers and in the set of integers. And second, commutativity and associativity are both closed downwards. Another exercise. Determine if each of the following semigroups is a commutative semigroup. Okay, why don't you go ahead and pause the video, try these two problems now, and then resume the video to check your answers against mine. The first one is n star, where a star b is equal to a. The answer to this is no. As a counterexample, we have 2 star 5 is equal to 2, whereas 5 star 2 is equal to 5. We're picking the one on the left each time. So when we switch the order, we might get a different one on the left. The second one, Z star, where A star B is the minimum of A and B. The answer is yes. There are two cases to check. The first is A less than or equal to B. In this case, we have A star B is the minimum of A and B, which is equal to A because we're assuming that A is less than or equal to B. That's equal to the minimum of B and A, which is B star A. For case 2, B less than or equal to A, we have A star B is the minimum of A and B, which in this case is B because we're assuming that B is less than or equal to A. That's the same as the minimum of B and A, which is B star A.